All right, so we'll start. Okay, so last week, in fact, we start to talk about a language to help us to analyze and to talk about the time complexity of algorithms. Okay, this is so-called asymptotic notions. Okay, what we're going to do today is that we're going to first review this and then talk about some of its property, go through a few more examples. Then we're going to start to use this language, this asymptotic language, to help us to analyze the time complexity of algorithms. Okay. Okay. So first, here's what we said last time. Okay. So essentially, this is a way for us to compare two functions, call it f and g. Okay. Compare these two functions, but we want to compare them in a way we want to see that as n is large enough, what's the relation between them, and we also want to ignore constants. Okay, as such, we have these three notations here. The big O essentially, f of n is in big O of g of n if, see whether you can see my cursor here, if essentially for n large enough, we have that f of n is always smaller than g of n up to a constant. Okay, so here's a pictorial image of it. So f of n is always below c times g of n. Okay, so intuitively, this is analogous to the two numbers, f is smaller than g, but here is up to a constant. Okay. Now, big omega says that, okay, when n is large enough, f is always bigger than g of n, okay, up to a constant. There is some constant to make this hold. Okay. Now, big theta essentially means that both the upper and the lower bounds hold, namely, for n large enough, f of n is smaller than c2 times g of n, but bigger than c1 times g of n. So intuitively, this means that f of n and g of n, these two functions, are kind of equivalent up to constant. So they're of the same order. That's what we often say. Okay, so there's they're asymptotically the same. Okay, all right. Now, we also introduce an alternative way to understand this notation is use the limit of the ratio f of n over g of n. Okay, in particular, so intuitively, if f of n over g of n is smaller in the limit, this ratio is smaller than c. What does that mean? That just means that f of n is basically smaller than c times g of n. That's why f of n is in the bigger of g of n. Same for bigger than c, and then the two has asymptotically tight relation, namely big theta relation, if in the limit. This limit goes into some constant between, this limit goes in between two constants, c1 and c2, okay? There's some useful special cases that in practice, when you try to understand the relations between two functions, this can be very handy. Okay, so for example, if f of n over g of n, the limit goes to 0, what does that mean? Well, this means that intuitively, when n is large, f of n is much smaller than g of n, so it grows much more slowly. Okay, so for example, n here, let me annotate. So for example, if you look at f of n equal to n, g of n equal to n squared, then the limit of n over n squared is 1 over m, which in the limit, it goes to 0. Well, intuitively, that's because f of n grows much more smaller than g of m. So this means, of course, f of n will be upper bounded than g of m. But in addition, we also know that f of n cannot be lower bounded by g of n because f of n is much smaller than g of m. As such, f of n cannot be in big theta of g of n. Okay, so another way to say here is that f of n is not in big omega of g of n. Okay, the opposite is that if f of n over g of n in the limit go to infinity, what does this mean? This means that f of n is much bigger than g of n when n become larger, and this difference become larger and larger. Okay, this means that, well, naturally, f of n is kind of bigger than g of n, so this holds. Okay, but at the same time, because this is infinity, this means that f of n cannot be bounded from above by g of n, because f of n is much bigger than g of n. So it's not possible that f of n, you can find a constant so that f of n is smaller than c times g of n. Okay, oops, it cannot be. And as such, f of n is not in the big zeta of g of n. Okay, and if the limit goes to, so the example for this one will be that if your f of m is n squared and g of n is m, then clearly this holds. Okay, now if the limit goes to a constant c, that means the two functions exactly a constant factor of each other, so they're asymptotically the same. So that's why you have this relation. Okay, so for these three statements, these are the useful special cases. Their converse do not hold for these three cases. Okay, it's just one direction. All right. Okay, so sometimes when we see time functions, okay, there's certain order among them that we call this hierarchy. Okay, so for example, the fastest algorithm, namely the smallest function, is essentially a constant function. Okay, and of course, I'm not giving the complete spectrum, but then logarithmic function is basically slower than constant function. So between any two of any two functions here, the relation between them is that the top function is bounded from below by the bottom function, but they're not equivalent. So they don't have the big zeta relation. Okay, so for example, function n is lower bounded by n to the power of 0.5, but n is not in the big zeta of. Okay, so as you go from bottom up, your function become bigger and bigger asymptotically. Okay, none of the two consecutive functions have asymptotically the same. Okay, so clearly log m, polynomial of log m will be bigger than log n asymptotically. Okay, any polynomial function will bigger than any logarithm function, even with an exponent, with a polynomial of logarithm function. Okay, so as the exponent goes bigger, clearly this one, the function become larger asymptotically. Okay, so linear function is more than square root of m. Now, between these two, the difference is that here you multiply by another increasing function n log n. That's why this is bigger than the bottom, and so on. Okay, any exponential function is asymptotically bigger than any polynomial function. Okay, so it doesn't matter what is this exponent. So we have the following: 2 to the m is in fact asymptotically bigger than n to the power, let's say 1 million. Okay, so any polynomial function is asymptotically smaller than polynomial function when n is very large. Okay, and if we increase the base of the exponential function, then the function grows asymptotically larger as well. So I have so these are some useful hierarchy. It's not complete, but you can see that how the functions become asymptotically bigger and bigger. Okay. So feel free to ask questions, okay, either in chat or just ask. All right, now let's just look at a few more examples before we talk about properties of this asymptotic. So let's see. The first one is this statement true? What do you think? You can just type in if you want. What do we have here? On the left-hand side, this is actually n to the power 1.5, right? And on the right-hand side, we have n squared. So clearly, this is asymptotically smaller than n squared. Okay, so this is true. Okay, how about this? Is this true? Well, here, this is only to the power 1.5, and here's a quadratic function. So this function grows much faster. So this one cannot be bigger than this function asymptotically. Okay, so you can prove this using limit. So this is not true. Okay, so this, as we already said, this is clearly logarithm function grows slower than the polynomial function. Okay, so this is also true intuitively. Any logarithmic function asymptotically grows slower than the polynomial function. So they're asymptotically smaller. Okay. Again, the reason is that if you think in terms of the limit, so if you have log m over square root of n, okay, what happens is that in the limit, okay, in fact, it doesn't even matter. Let me actually erase this here. Oops, okay. So in fact, this can be any polynomial function for a bigger than 0, okay? So logarithmic function divided over polynomial function, okay? In the limit, when n is very large, this is always goes to 0, okay? Which means that this always, we know that log n is, and this always true, okay? All right, now if we compare this to, well, intuitively, the left-hand side, so, if we take the limit of this, we have n log n over n 1.5, which is log n over square root of n. We get what we had before. We know that in the limit, this is 0. That's why this is also true. Okay? Okay, so in the homework, you have some problem where we ask you that we give you a function on the left-hand side, and then we ask you to write its asymptotic time complexity. We ask you to simplify it as much as possible. Okay, so what it means that in the end, you should just have one term of the form a polynomial function or logarithmic function or exponential function. Okay, so for example, in this case, we look at this, we recognize, okay, the dominating term is really quadratic. All of this are going to be much smaller than n squared asymptotically, okay? So as such, asymptotically, this is the same as n squared, okay? So in the homework, this would be the answer that we hope that you're going to write. This also to demonstrate why we want asymptotic language, because this helps us to simplify a seemingly complicated function, okay? All right. All right, let's look at the last one. What do you think? Is this one true? So here, we're using this one as example where on the left-hand side, even though I have this huge number, 10 to the power of 10, okay, but up to constant, the left-hand side is still just a linear function. Well, okay, well, on the right hand, I have a quadratic function. So clearly, linear function is smaller than quadratic function. Okay, so even though that, so the point of this is that sometimes don't get confused by huge constants. Constants do not really matter in terms of asymptotic language. Okay, so this essentially is saying that it's linear function in the big O of quadratic function. Of course, that's true. Okay, questions? All right. Okay, now I want to state some useful relations that are not just for right now when we look at asymptotic language, but later when we analyze algorithms in this course, this are useful to know, okay? So I mentioned this before. For any two constant a, b bigger than 1, okay, what we know is that, so essentially what this is saying is that logarithmic functions, doesn't matter what their base is, okay, they differ only by constant factor. That's why all logarithmic functions are asymptotically the same, okay? Now, the formal way to prove this was that we know that given this function, I can use change of base formula to write this to be okay, which means that now this is written as now this, I don't care what that is, but this is a positive constant, okay? That means that the function f of m and the function g of m only differ by a constant. As such, they're asymptotically the same. Okay, as such, I can also write that very often in our time complexity, and then just choose the log n base 10. I use that because the base doesn't matter asymptotically. Okay, all right. Now, the second useful, a second group of useful relations is that, so if I have 1 plus 2 all the way up to n, okay, this is just arithmetic sum. So we can write out the precise formula. Well, in this case, we can write it out, which is n plus 1 over 2. And thus we can see that the dominating term is n squared. That's why that this gives us asymptotically same as n squared. Okay. Now it turned out that this actually generalized to different exponents. Okay. If instead of 1 plus 2 plus 3 plus n, you will do 1 plus 2 squared plus 3 squared plus 4 squared up to n squared. Okay. It turned out that this actually is the same as asymptotically. This is the same as n cubed. Okay. Now, in general, if you raise it to power d, 1 plus 2 to the power of d plus 3 to the power of d, and so on, then you get asymptotically, this is the same as n to the power of d plus 1. Okay. Now, just to give you an intuition why this is a case. Okay, so I'm not going to just prove this very formally, but just to show you intuitively why this is the case. Okay, so let's just use this one as an example. The same argument works for the general case. Okay, what do I have? We have that. So to prove that this is asymptotically the same as n cubed, that means that we need to find, we can both bound it from above by n cubed times a constant, and can also bound it from below by n cubed by a constant times a constant. Okay, the upper bound is very easy. Why? 1 plus 2 squared plus 3 squared plus all the way to n squared, clearly smaller than n squared plus all the way n squared. Namely, I just replace every one by n. They're only getting bigger, okay? And the number of terms here is n. As such, we have this exactly is n cubed. In other words, this is smaller than n cubed. So we get the upper bound. So this implies that 1 plus 2 squared plus 3 squared all the way to n squared is in big O of n cubed. Okay, so the upper bound is the easy one. Now let's say that we want to prove the lower bound. Okay, this is a little bit trickier, but with a nice trick, it's easy to see as well. So we have now 1 plus 2 squared plus all the way plus n squared. Now, I cannot do the same thing anymore. I cannot say, okay, all of this, each of the term here is bigger than the smallest. So they're all bigger than 1. Because if I do that, I can say, okay, this is bigger than 1 plus 1 plus 1 plus all the way. Okay, because each term is bigger than this. This is correct. But this will only give me, since I have n terms, I would only get n squared. And this is not, we cannot prove the lower bound using this way. Okay, so this is too loose because we throw away too much. Okay, so instead, the intuition is that, can I somehow use a tighter way to bound from below? Okay, so we see that if we consider we go, as we do the addition, at some point we get to plus n over 2 squared and continue, okay? Now, if I only focus on this half, I ignore everything in front of it. So this is bigger than n over 2 squared plus n over 2 plus 1 squared plus all the way to n squared, okay? We see for each of this, now we can use the smallest one because the smallest one intuitively is also of the order of n. So now we get n over 2 squared plus n over 2 squared plus all the way n over 2 squared. And how many terms do we have? We have going from n over 2 to n. So the number of terms is n minus n over 2 plus 1. That's the number of terms we have. Okay, so that means that this, we're just adding n over 2 squared up by this number of times. That's the number of terms we have. So that's why we have n over 2 squared times m minus n over 2 plus 1, which is n over 2 squared times n over 2 plus 1. Now, clearly, this is basically n cubed because I have n squared times m, and so this is bigger than n cubed divided by 8. Okay, so now we show that the sum is bigger than n cubed times another constant. Okay, so this proves the lower bound. Okay, so this implies 1 plus 2 squared, 3 squared is bigger than since it's bigger than n cubed over 8, that means that this is in. Okay, so we proved both upper bound and lower bound. As such, this one holds. Okay, so this kind of splitting sum trick, it's used very common to establish the bound. Okay, all right. Now, another useful relation is that if you have log 1 plus log 2 plus all the way to log n, now because log a plus log b is the same as log a times b, okay? So that equivalent boils down to be log of 1 times 2 times 3 times 4, which is n factorial, okay? And it turns out that n factorial essentially is kind of related to n to the power of n. That's why when we take the exponent to the front, we get this. Okay, so this is a very useful, more precisely, we should use some inequality called the Stirling inequality. But this is a very useful factor that we'll use later. Okay. All right. Another useful relation is coming from geometric series. Okay. So intuitively, if I have a series, now it's actually the exponent keep changing. So let's say we have 1 plus r squared, and then all the way till r to the power of n. Okay, the general formula is this. This is what we have. Okay, but what this boils down to, what this gives us, depends on whether r is bigger than 1 or r is smaller than 1. Okay, so for example, if r is smaller than 1, then we note that as m increase, this become very small. This is something smaller than 1. It is eventually just become, this is smaller than 1 over 1 minus r, which means it's a constant. Okay, so then we get it's a constant. So what I have here is a special case when r equal to 1/2. Okay, so 1 plus 1/2 plus 1/2 squared, and all the way equal to, in fact, this is smaller than 2. That's why it's a constant. Okay, but if r is bigger than 1, okay, then you cannot throw away this anymore, because now if r is bigger than 1, as the exponent become larger, this one become larger and larger, go to infinity. Okay, so now what you have is that you have this quantity, and this is constant, this is constant, so what dominates is r to the power of n plus 1. Okay, so for example, if you have 1 plus 2 plus 2 squared 2m, then this is dominated by 2 to the power of m plus 1. Okay, so this geometric series is also something we'll use very common. Okay, in particular this one. Okay, now I want to say a little bit more about this. So this essentially is saying that, in fact, if you only look at, let me remove this. If you only look at this part, okay, you can let m goes to infinity. You keep halving it. Okay, what it is saying, it says that imagine that you are at point A, so you are at point A, you want to go to point B, whose distance is 1, the distance between them. Okay, so let's say that we do the following. I say that, okay, first I take a half distance, so this is 1/2. I take a step size of 1/2. Then I take 1/2 of the remainder, which is 1/4. Okay, so I try to get to B, but every time my step size, I shrink it by half. Okay, so next I shrink my step size by another half, 1.8. Now, as you can see, if I do this, since every time for what remains, I only take half of that as a step size. Okay, even as I take the steps infinite number of times, I just get very close to B, but I never really reach B. Okay, which means that 1/2 plus 1/4 plus 1/8 plus 1/2 to the 4, and so on. In the limit, this one is 1. Okay, but it's never goes above 1. Okay, that's why this whole thing is smaller than equal to 2. Okay, that's just a geometric intuition. Okay, so give you only constant. Okay. So intuitively, why is this happening? This is because that when every time you take a ratio of what you have before, you're reducing the size very fast. Even though you can add m can be infinite. Okay, even if you add infinite terms, but what you're adding is getting smaller and smaller very fast. So even though you're adding infinite term, still the whole thing is never more than a constant. Okay? All right. Questions? Yeah. So right now this looks a bit dry, but then when we later do the analysis, we'll see that this series would come out naturally. Okay. Okay. Now let's talk about a few properties of the asymptotic notation. What I'm not going to prove them formally. I just want to give you the intuitive idea why they hold. Okay, so all of these properties in some sense are quite intuitive. Okay, so well, the first one is straightforward because just by definition, if Fn is in the big theta of g of n, essentially that means it's both upper bounded by g of n and it's also lower bounded by g of n. Okay, this is just coming from definition. Okay, so here what we have is that if you this big theta relation is symmetric. So if f of n is asymptotically same as g of n, naturally g of n is asymptotically the same as f of n. Okay. Okay, and if f of n is bounded from above by g of n, so intuitively the smaller than or equal to, then naturally that means g of n is bigger than or equal to f of n. Okay, so and the converse of this also hold. Okay, so what this, using a concrete example, what does this mean? So for example, if I say that m linear function is at most n log n, clearly n log n is bigger, right? So that also implies that n log n is bounded below, from below by n. Okay, it's okay. Again, it's useful to think in terms of using the analogy that smaller than equal to, bigger than equal to of numbers. Okay. Also, we have that if f of n is smaller than or equal to g of n, is bounded from above, and g of n is bounded from above by another function h of n, then f of n is also smaller than the third function. So intuitively, what are we saying? So if f of n, this is f of n. Okay, if f of n is smaller than, say, c times g of n, okay, so it's below g of n, and if g of n is smaller than some c prime times h of n, then clearly f of n is smaller than h of n. So that's why we have this relation. Okay. Then this is useful, this is transitivity, because if I know that, say, log n is smaller than m and n is smaller than the exponential function, then naturally log n is bounded from above by the exponential function. All right. If I ask you to prove this, okay, so some statement, for example, prove that if f of n is in the big theta of g of n, then g of n is in the big theta of f of n, then usually you always go to definition. Okay, so what I put the proof here, but it's rather straightforward, so I will not go over that. But essentially, what this means is that you have to go through the definition. If we know that f of n is in the big theta of g of n, that means that we know this holds for some constant. Okay, and what is our target? Our goal is to prove that there are some other constants so that this relation holds, because this would then implies g of n is in the big theta of f of n. Okay, so then what you need to do is to convert from this relation, using this relation to help you to get to this relation. Okay, and that is not very hard. You just need to take this two inequality and then flip the constant. Then you get this inequality. Okay, So you can take a look at this proof offline. My point here is that even though that this is very intuitive, but if I ask you to prove formally, you always go back to the definition. Okay. All right. So here are some other useful properties. Again, this is actually useful when you are given a complicated function and you want to simplify it to find what is this, what is equivalent to using the asymptotic language. Okay. So if I give you two functions and I add them up, okay. Now what this is essentially saying is that basically the bigger function dominates. Okay. So the sum of these two functions is asymptotically the same as the larger function. Okay, so this is essentially saying the same thing because f of m plus something which is asymptotically smaller than that, then the sum of them will still be of the same order of f of n. Okay, and I can go one step further. If f1 of n is asymptotically the same as g1 of n, and f2 of n is asymptotically the same as g2 of n, then the sum of these two functions is essentially the same as asymptotically g1 plus gn. Okay, so this is useful when we try to analyze algorithm with multiple commands. Just give you one example. Let's say I have a very artificial algorithm here that this function foo calls two other functions. One is called bar, one is called bus. Okay, so now what does this mean? This means that the time complexity of function foo is equal to the time we need to spend for the first procedure and then plus the time we need to spend for the second procedure. Okay, all right. Now assume that the first procedure time is actually theta of n squared. The second one is n cubed. Now what is the total time? Well, the total time as such is basically theta of n squared plus n cubed. And we look at this two, now we go to this. Then we only need to focus on the dominating factor, the one that's larger. Okay, so this is the same as theta of n cubed. Okay, so these relations are very useful for us. Essentially, they satisfy the intuition I mentioned at the beginning, where the big theta relation lets you ignore the lower order terms, okay, and also constant. Okay, because the lower order term, they are basically not dominating. Okay, so if you have a function, a dominating term plus some lower order term, you can ignore them. It's asymptotically the same as the function itself. Okay? All right. Okay, I should point out that this language primarily is developed to talk about complexities, whether it's time complexity or not. So in fact, without saying it explicitly, all the functions that we consider in this class, we assume that they are positive functions, okay? Because if it's a time complexity of an algorithm, it cannot be negative running time, okay? All right. Okay, another relation that we have is that very similar to the addition one, okay, very similar to this addition one, we also have the multiplication version, okay? So if f1 of n is in the big theta of g1 of n and f2 of n is in the big theta of g2 of n, then the multiplication of them is the same as theta of this two, okay? So what does this mean? This means that if I give you a complicated function, then I can use this to simplify. So just an example, let's say that I have the following: 3n cubed plus n squared times log m plus 10. So I say that simplify this function to be as simple as possible, okay? You don't want to multiply them out and then do this. What you recognize immediately is that, okay, this first term, you can think of this as f1 and of n, okay? You immediately see that this one is actually big theta of n cubed because we said that the dominating one matters, okay? And the second one, the dominating one is log m. So this is same as okay? So you write this is your answer and you cannot go any simpler than this, okay? So this is what we have, all right? Okay, so this is how we use. So essentially, this property may look very boring, but essentially what it tells you is that you are safe to when you have different terms together. If they're additive, if you add different terms together, then you can look for the dominating term, okay, the one that grows fastest, the biggest one. Or if they multiply together, you can just simplify each of them independently and put them together, okay? So this helps you to break things down. All right. Okay, so here's just another example. So if I ask you to analyze the time complex of this algorithm, you recognize this takes time constant, and how much does each of the inner loop take? Well, this one, the iteration is basically this takes c times n squared minus 100n, because that's the number of iteration. Okay, then the outer loop. How many iterations does the outer loop run? Well, it runs in 4n squared plus 5 subtract 4m minus 4, okay, which is 4n squared minus 4m plus 1. Okay, so that's how many iterations of the outer loop. Okay, so the total time complexity is the number of iterations of the outer loop, which is times the cost of the inner loop, which is c times n squared minus 100n. Okay, asymptotically, what's this? Does anyone want to tell me what asymptotically, what's this? If I simplify this, what do I get? We have n squared times n squared. This is what we have. Okay, so just using the trick that we had before. Okay. Now, as I mentioned that we introduced this asymptotic language to help us to measure time complexity of algorithms, also maybe space complexity of algorithms. But the use of this asymptotic language goes beyond just analyzing algorithms, okay? So that you can use it in other places where when you want to focus on the measurement of the growth rate, okay? So for example, if I want to have some idea what this sum gives me, okay, but I mean this log of n factorial is a very complicated number, but I just want to know roughly how big is it? Then using this tells me, okay, this essentially grows like n log n, okay? Or in your 40A, we talk about the central limit theory where if you have the sample mean has a normal distribution with standard deviation of sigma of the square root of m, okay, we often say that the error, we don't want to precisely specify what is this sigma, what is the other constant involved. We can just say that the error in the sample mean is the order of 1 over square root of n with high probability. Okay, so what I'm saying here, the precise example is not important. Just I'm saying that this asymptotic language can, in general, help us to give us some idea what's the order of the scale of your function of the function of interest. Okay. Okay. Now we have to. There's some. We also have to be careful when we use these terms. Okay. I keep saying that it's convenient to think that a big O can be sort of as smaller than or equal to, okay, when you compare numbers. Big omega is basically says bigger, one function is bigger than or equal to the other function, okay? And the big theta means that they're roughly the same up to constant. It's kind of similar to equality, okay? But these are functions, there are constants involved. So all these relations holds modular constant factor scaling, okay? That's why that I can say that the n is in the big theta of 100n, okay? Even though that clearly they're not the same, and n, in fact, is smaller than 100n, but up to constant, they're about the same order, okay? So that's one thing we have to be careful. Second is that if I give you a pair of numbers, you can always compare them. One of the relation, bigger than, smaller than, equal to, has to hold. Okay, but this is not true for functions. Okay, your two function, maybe one function goes like this, that's your f of m. Maybe the other function g of m somehow just keep going up and down and become bigger and bigger. So this two, you never really have any relation but you don't have to have this asymptotic relation between two functions. Okay, so that's one thing to be aware of. Okay, not every pair of functions have such relations. Okay, it could be that none of the three relations holds. Okay, and because of that, if we say that f of n is not bounded from above by g of n, okay, if it's numbers, if I have two numbers, if I say a is not smaller than equal to b, then this must imply that a is bigger than b, right? So for numbers, okay, because two numbers have to have one of the three relation, okay? But here, if f of n is not bounded from above by g of n, this does not mean that then it's bounded below by g of n. It's possible that these two functions do not have any relation at all, so none of these two hold. Okay, so somehow, let me see, is there questions here? Because here I see something, but I don't see it here. Okay, all right. So if someone put in the chat window a question, you can just let me know. Somehow on my tablet, I don't see this anymore. Okay, all right. Okay. Okay. Now, we like this asymptotic language because it gives us a quick intuitive idea of how fast your algorithm is, okay? So if I say, oh, my algorithm is 100n squared plus 50n square root m plus 5n and so on, this looks too complicated, okay? So using asymptotic language, I can just say, hey, my function runs in quadratic running time, okay? So it's convenient that way, okay? And you can also use this to compare different algorithms for the same problem. Let's say that for sorting a list of n numbers, you give an algorithm that runs in this time, and then someone else given an algorithm that runs in 100 n log n, which is n log n. Then I immediately see, okay, n squared is asymptotically bigger than n log n. So this is a better algorithm because it runs smaller small amount of time. It's faster. Okay? But at the same time, that said, we also have to be conscious that when we use this asymptotic language, this big O, big omega, big theta, they're actually hiding constant inside. And how big that constant, we don't know, okay? Because, so for example, if you give an algorithm, so this is algorithm 1, this is algorithm 2, okay? On the surface, if we compare this to asymptotic complexity, we say, hey, this is a better algorithm because it only runs in linear time while this one is n log n, okay? But what if actually your algorithm, the true running time is say 10 to the, it's 1 billion times n, while this algorithm is only n log n, okay? So if that's the case, and the T2 of n is n log n. Now, even though that asymptotically T1 is faster than T2, okay? But you can ask that for what value of n will it become faster? Well, this is only smaller than this if log n is bigger than 10 to the 9, okay? What does this mean? Log n is bigger than 10 to the 9 means that n is bigger than 10 to the power of 10 to the 9, which is huge, okay? So you're never going to see a practical data set of this size, okay? So what we're saying is that asymptotic languages tells you that one function is better than other when the size of the data become very large, become large enough, okay? But exactly what is that large enough? That depends on the constant you have, okay? And if the constant is really bad, actually a linear time algorithm could be worse than an n log n algorithm, okay? Now, in this class, usually we focus on asymptotic language. If it's better asymptotically, we say this is a better algorithm, although you should be aware of this constant, the hidden constant, okay? So in practice, sometimes certain algorithm which may not look faster, actually people prefer that because it runs better on practical data sets, okay? All right. Okay, another thing is that we like this language, and usually we use this one to help us to simplify things, okay? So if I write this function, we write that this is in the big set of 3n squared, okay? This is not wrong, it's a correct relation, okay? But this is not great, we don't like it because this kind of beats the purpose that we try to simplify the time complexity, okay? So this is a better one, because this immediately point out this function is grows like a quadratic function, okay? And there also people sometimes people tend to think, okay, if this is a big set of n squared, that means that this my function is basically of this form. It's at most n squared. So this is not necessarily true. You could have other ugly terms there too. They don't have to be polynomial. They can have anything as long as asymptotically, this is still the dominant n squared is a dominating term. Okay, so these are all minor things. One last caution. I said earlier that if I add two functions, so if I have a function which is big or smaller, at most runs time is a linear time function, and another linear time algorithm, together they still runs in linear time. Okay, intuitively you can think this is at most a 2n. Okay, so this is good. Okay, but if I look at this, if I add this one k times, is it still true that this is same as n plus big O of n? Well, this is not true anymore, okay? Because what happens is that this is really, so this is not true, because this is now m plus, really what you should write is k times m. If k is a constant, then this is same as order of m. But if k is not a constant, say, what if k equal to, say, square root of n? Okay, in that case, then what you have is that t of n is order of kn, which is order of n times square root of n. Okay, so when we say that we can add terms together and still the biggest one dominant, then assuming we only added them constant number of times. Okay, because if you add n linear times, then you of course get n squared, get the quadratic. Okay, so just be careful of that. Okay. All right. Other questions before we move on to look at the time complexity of algorithms? Okay, now if there are no further questions, let's now talk about how to use this language to help us to analyze complexity of algorithms. Okay, so let's first look at a very simple example. Here we have, it's easy to see this code is just computing given an array. So this is an array of certain numbers, okay? So then we're simply starting with total initialized to be 0. We just go through all the elements in the array and sum it up, okay? And in the end, we return the average of it. In other words, we're returning the mean of a set of numbers stored in the array, okay? All right, so time complexity of this. What does it mean? So time complexity means that if we assume that the input is of size n, for any input of size n, what we see is that, well, I have to go through every element in the array. So I have to, the for loop runs in n iteration, where n is the size of the array, okay? As such, the whole time complexity is c times n, which is big theta of n. Okay, now when I say that, note that this actually holds no matter what the input is. If the size is n, then this algorithm takes time, which is linear in n. Okay, all right. But if we look at the following algorithm, this is another important operation that we tend to have, which is called a search query. Okay, so imagine that you are given a database of all students, okay, and each student is indexed, is represented by the key, the student ID, okay, which is, can think it's a number, okay. Now I want to search whether a specific student is there in the database or not. So given this key, the query, it's called search query, is asked that tell me that whether this key is in the database, and return this key if index of this element in the database if we find it, otherwise return none. Okay, very often this database can be represented as an array, let's say. Okay, so in this case, we have the array representing database. Now, what do we do? The input is an array and your key that we're going to query for, we're going to search for. Okay, so what we do is that we go through every element in A. So X is every element in A, and I is its indices. Basically, I equal to 0, 1, 2, 3, up to n minus 1, if n is the size of the array. Okay, and if it turned out that this element equal to the key, okay, we're looking for, we immediately return the index. And if we couldn't find it in the end, then we return none. Okay, so now I ask you, given the array A, what is the running time of the algorithm? Okay, now you have to think now, because in fact, for specific input, the running time of the algorithm may not be the same. Okay, so what does that mean? Because we return whenever we find the key, right? So if we find it faster, then we return earlier. If we couldn't find it, then we have to go through every element in the array and then return, which is going to take a longer time. Okay, so in other words, now the running time depends on the specific input. So now we have a choice because the running time is not the same. We could talk about what is the best case. You know, what is the case that we're really lucky is the best case, best scenario. So in the best case, what do you think is the running time of this algorithm? So what is the best case? What's the best case scenario? Well, in the best case, we look for the key, and the first element we checked in the array is the key we're looking for. So we immediately return, right? So the algorithm only check one element in the array and takes only constant time. So that's the best case, okay? But in the worst case, then we're not lucky. Maybe the key is not even in the database. We have to go all the way, search through the entire array, go through this entire for loop, and then return none, which means that in the worst case, we have to check every element in the array. If the size is n, then the time complexity is order of n. Okay, so we have different scenarios. We can have best case and worst case. Okay, now, and that means that we can talk about the best case time complexity and also worst case time complexity. Okay, so what is the best case time complexity? It basically says that how does the time taken in the best scenario grow as the input gets larger? Namely, your input this is a function of n, where n is size of the input. For each of the n, this t best of n tells me the best time of the algorithm over any input of size n. Okay, and the asymptotic growth of this is the asymptotic notation of this best case time complexity. So for example, in the previous, this linear search algorithm we just saw, okay, no matter what your input size is, in the best case, I immediately return because I immediately found it. So the best case time complexity is constant. Okay. However, note that for the other function, the one compute the mean, for that algorithm, okay, for that one, what is the best case scenario? Well, that function, we are computing, we have to visit each element in the input array and then sum it up and then average it, right? So it doesn't matter what your input is. We still have to go through every element in it and then sum it up, which means that even in the best case, the time complexity is still linear for that one. Okay, but for the linear search one, there can be a difference. Okay. All right, so this is the best case time complexity. Worst case is analogous. And now we say that, okay, how does the time taken in the worst case grow as the input gets larger? Okay, in particular, this t worst of n is that for any input of size n, what is the worst time the algorithm would take? Okay, and asymptotic growth of this will then be the asymptotic notation for this. So now for the previous linear search algorithm, the best case, we immediately return, that's constant. But in the worst case, okay, in the worst case, for any input of size n, in the worst case, the key is not in. So we have to go through all the elements. So in the worst case, it's a linear time algorithm. Okay? All right. Now, often in the practice, okay, and also most of the time later in this class, okay, we actually focus on the, people like to talk about the worst case time complexity. Okay, why? Because if I give you an algorithm, okay, worst case basically says that even in the worst possible scenario, your algorithm is still, if I say that the worst case time complexity of my algorithm is linear, what that says is that even in the worst case, whatever input you give me of size n, okay, still my running time can never be more than constant times the input size. Okay, so then you have confidence that no matter what happens, okay, for all possible input, the time complexity of my algorithm is good, bounded by this value. Okay, so that's why very often we talk about the worst case behavior of an algorithm. Okay, on the other hand, in data analysis, okay, sometimes your input data, the worst case may happen, but then maybe that only happen when your input is really weird, when your input is very, very unnatural. Maybe most of your input coming from a specific form. Let's say you have points coming from a certain distribution. So most of the input is, concentrated around the mean of that distribution, okay? But so in this case, you can also talk about what is the average time complexity, which we're going to talk about next time, okay? Or you want to know that what is the, to have a better understanding of the performance of algorithm, I want to know that how fast can the algorithm ever run if we get lucky, so in which case you want to know the best case time complexity, okay? But still, I would say that in practice, okay, best case is just for you to get some idea of your the real lucky situation. In general, the worst case time complexity analysis and the average case time complexity analysis are more prominent in practice. Okay, with the worst case, give you a confidence of the worst, even in the worst case, you have confidence this algorithm is efficient. Okay, while average tells you that in general, on the average case, how does the algorithm perform? Okay, so those will be what's usually used in practice. Okay, all right, but let's look at another example here. Let's say that the following, the movie problem. You're in the flight, you are given a list of movies, each one has a specific length, okay? There's a stored in an array called movies, okay? And the flight duration is D, okay? So what you want is that you want to find 2 movies whose total time exactly matches the flight duration. So you don't waste any extra time and you also don't miss any parts of the movie, okay? And if you can find that, you want to search, and if you can find that, great. If not, you return none. So that's what you want to have an algorithm to do, okay? Again, we said that what is the most straightforward idea to handle this, to solve this? Well, I have a list of n movies. I want to find 2 movies to see whether their time adds up to D or not. The most straightforward way to do that is I kind of enumerate all possible pairs of movies and then check whether we get it or not. Okay, so here's the pseudocode for what I just said. It's a very simple approach. Okay, so you let n denote the length of the movie. Then the first movie, this is I. So you first go through for each of the first movie. For the second movie, you don't have to go through the part that you already seen that the first movie covered. So the second movie goes from all the remainder of the list. Okay, so the first one goes from 0 to n-1. The second one goes from I plus 1 to n-1. Okay, then this basically enumerate all possible pairs of movies. Okay, then for each such pair, you say what's the length? If it's equal to D, we return it. Okay, otherwise we continue. If in the end we enumerate all possible one, we still didn't find it, then we return none. Okay, so that's the algorithm, very simple. Okay, now what is the best case scenario for this one? Well, similarly, the best case is that we got really lucky. The first pair we're checking, okay, when I equal to 0, j equal to 1, happen to be already the total length equal to d. So we found such a pair, so we immediately return, okay? So that means that the best case time complexity is constant again in this case. It's not always constant, it's just in this case it's also constant, okay? What is the worst case time complexity? So with the first homework, I assume at this point it's easy to see. We have two for loops, okay? The second one, the time is actually, so in fact, let me write it here. So let me first clear this. Let's now look at the worst case. So you always go inside out, okay? So you for each of the inside, you say that basically you never return till the end. That's worst case. So this is a constant. And how many iterations? We have n minus I number of iterations for the inner loop. That means that the inner loop takes time for fixed I. The inner loop takes time c times n minus I. Okay? What is the total time? The total time is basically for outer loop where I changes. So what we have is that I changes from 0 to n minus 1, and inside the time is n minus I. Okay? So if I take c out, this when I is 0, we have n plus n minus 1 plus, so this is I equal to 0, this is I equal to 1, all the way to n minus 1, which is 1. So what we have is c times 1 plus 2 plus 3. I simply inverted the order here. So this is arithmetic. This is arithmetic series, and this gives us quadratic. Okay, so the worst case is basically quadratic mining time. Okay, all right. Okay. Now, the algorithm that I give is a very straightforward, simple algorithm. Okay, I would like to ask you to think whether you can find an algorithm that can do better, that has a better worst case time complexity. Okay, in fact, I think in your homework there's a problem along this line. Okay. Of course, I mean, it's not always true that even though in the two previous examples, the best case time complexity is constant, that's not necessarily true. Remember, the mean algorithm best case time complexity is the same as the worst case time complexity, okay? So the best case time complexity really is about that for what structure of the input that happen to make the algorithm execute faster, okay? So for example, for the search case, if your structure of the input is that the number that you're looking for happens just to be the first of your input, then that's when you get the best case. Okay. In general, the knowledge of best and worst case, both of them can give you a more thorough understanding of the performance of the algorithm. You know that if you get really lucky, what is the, if even in the best case, suppose best case is in the worst case is the same, okay, that means that this algorithm basically on any input would run in a certain amount of time, okay? But as I mentioned that both best and worst case can be biased by only some very specific input, which may be very infrequent, okay? So just because that the worst case time complexity of an algorithm is say n to the power of 10, okay, doesn't necessarily mean this is a bad algorithm. It could be that there's only one input that would really make this algorithm run very slowly, one type of input, that would make the algorithm run very slowly. But maybe that in practice, most of the time, more than 99.99% of time, your input is not of that type, which means that the practical performance of the algorithm can still be very good. Okay, so from this sense, that's why, as I said, that it makes more sense to talk about in practice also the average or expected running time. Okay, which we will formally talk next class. But since that I finished a little bit earlier today, let me actually start with the expected running time, because the next class has a lot of material anyway. Okay, all right, so let's see. Where is the okay, all right, so now you see them. Okay, so let's actually get started with this expected running time. Okay, now let me, so the first 2 weeks, so this is, we are focusing on the asymptotic language and analyzing the time complexity. So this may seem a bit more, the first 2 weeks a bit more mathematical than later. Okay, starting from next week, okay, next Tuesday, we'll start to talk about the problems and the designing algorithm for that. Okay, but this week, including Thursday's class, we're still going to talk about just the analyzing algorithm, the time complexity analysis. All right. Okay. So now we said that in practice, people like worst case, because that tells you that what is even that give you confidence of the performance, give you guarantee of the performance of your algorithm. Okay. And it's also good to know the best case, although not as essential, okay? But both worst case and the best case can be biased by some specific input, may not give you a feeling about what is the general performance of the algorithm, okay? So it's natural to think that how about average time complexity, okay? So intuitively, if your algorithm works on many different type of input, what is the final average time? Okay, so this gives you an idea of how your algorithm works on a typical input, so to speak. Okay, but there's a caveat. It's not so easy, because if I want to talk about average time complexity analysis, I have to assume that I know what is the distribution of all possible inputs. Okay, so if you know that, if you say that, okay, my input is going to be of the distribution is going to be this, then we can compute that for each of the input, what is the time complexity, and then what is the probability, what's a fraction of the time that this input is going to happen, okay? Because some input may happen more often than others, right? And then you can average it out, okay? Now, doing such analysis, sometimes we call this probabilistic analysis, okay? So this basically gives you this average time complexity, but you have to assume that we know what is the distribution of the input. Okay, we're going to see an example in a minute, okay? Alternatively, okay, there's another family of algorithm, which is so-called a randomized algorithm. What this randomized algorithm does is that your input, I may never know what is the distribution of the input. Okay, if you are handling data of patients coming from, say, San Diego, okay, prior you have no idea how that distribution would look like. You don't know that distribution. Okay, so we cannot assume that we know it. So randomized algorithm says that, okay, your input can be anything. Okay, but in the algorithm, I'm going to add a little bit randomness. Okay, once I add the randomness, now we're going to see examples. Now, even for the same input, your algorithm may run in different running time, but now I can analyze what is this expected behavior. Okay, the advantage of this is that you may have, if I give you a certain algorithm, there may be bad input. Okay, but now I add a bit randomness inside, I can destroy this bad input using the randomness in the algorithm. So that's called randomized algorithm. Okay, so I'm going to see examples in a minute. All right, so let's start with a simple example. Okay, let's look at this. Again, the same linear search problem. Okay, we're given an array of size n and a key. And our goal is to search whether the key is inside or not. Okay, if we cannot find it, we return none. Okay, what is the worst case time complexity? We already said. In the worst case, I have to enumerate every element in the array, check whether it's the key k or not. So that the worst case running time, it takes, for input of size n, it takes linear time. Okay. Now I ask, what is the average running time of this? Now we have to assume what is your input distribution. Okay, because then what does it mean by having the average? Okay, in particular, in general, you can think that the average running time is computed as follows. Okay, so I'm using this one to denote either the expected or average time, running time. Okay, so let's say that this is the probability of so if I have all possible input, okay, if I know the probability of each input, and I know what's the running type of my algorithm on that input I, okay, the type of input, okay, then I basically, the running time is that I take the running time on that specific type of input and I multiply by what's the probability this input would occur, then I sum it up. Okay, this is the same as when we compute expectation, okay, for given input. I'll update this later, okay? But to do this, I have to know what is this probability, namely, we have to assume a probability distribution on the input, okay? So here is one way of, for the linear search algorithm, okay? If we look at the running time, okay, what our input is the key k and the array a, okay? How many different type of inputs can we have? Well, it could be that the cases, basically we can think that the cases is that this key that we're looking for can be not in A, okay? Or it can be at k equal to AI for I equal to. So either the key I'm looking for is not in A at all, or the key I'm looking for is in the ith position of your array. Okay, so I figure out that this is a different possible cases for my input. Okay, is that questions? Okay, now but I need a way to assume what is the probability for each of the case. Okay, now let's assume a simple model. Okay, let's assume that in fact the key I'm looking for is definitely going to be in the array. Okay, so it's not the probability that the key is not in the array is 0. Okay, then let's assume that all permutations of the input is likely, which means that my key could, with equal chance, can be any position in the array. Okay, so this is kind of, you think that your input is somewhat uniform. Okay, so if this is the model that we assume, then what is the expected running time? Well, the expected running time, as we said, is that for each of the case, you figure out what is the time, then you multiply with the probability that happens. We have altogether n+1 cases. Either key is not in A or key k is in the ith position of the array A. So this is this is the expected running time. This is all the cases. Okay. Now under this model, the probability that the key is not in A is 0. So we have 0 plus, now for each position of the, so here I'm using the standard way of an array where it's the index from 1 to n, okay? So now we say that the probability that the key k is in the ith position, it's the same for everyone. That means this is 1 over n times. Now, if the key is at the ith position, what is the running time of the algorithm? Well, the algorithm just linearly scan the array till we find the key, right? So if it's in the ith position, then we only need to scan I number of items in the array. So time complexity is C times I, which means that our time is C over n summation of I for I goes from 1 to n. Okay, now what is this? This is arithmetic a sum. So this gives us as such the whole thing, this multiply with C over n, so n cancel, we have. Okay, so under this model, this of this input distribution, the time complexity is still linear. Okay, so this is the details also on the slides that you can find later. Okay, but let me point out that this is under the specific distribution. Okay, if I now assume something really weird, okay, so if just to make the point, go to the extreme. This is not realistic. Okay, if I assume that my input actually is the following, if I assume that the probability that the key you're looking for is in the portion of the array from 10 onwards to n. Let's say this probability is super tiny. It's only 1 over n. Okay? While for all the remainder case, let's say equal to 1 minus 1 over n. And all other case, the probability is 0. Okay? So in other words, what I'm saying that most of the time, almost all the time, the key you're looking for is the first element. Okay? This is not realistic, but let's just assume this is the input distribution. And then with some tiny probability, it may come some, in fact, let me make this easier just so that k equal to a n is 1 over n. Okay, so most of the time, your input is the key you're looking for is the first element. With tiny probability, it's the last element. Otherwise, it cannot be any other element because it's a very skewed input distribution. Okay, but under this distribution, what is expected running time? Well, the expected running time now will be this is 0. And here, most of them are 0. There are only 2 cases which is not 0. One is that 1k equal to 1. So in this case, the probability is 1 minus 1 over n. But the time in this case is constant because I return immediately. Okay? Or k equal to the last element. And the probability that happens is 1 over n. And the time in that case, I have to do a linear scan. I have to scan through the whole entire array. It's this. So then this adds up. This is constant. This is constant. So the whole thing is only constant. So for this really weird distribution, which we may never see it in practice, the average running time is only become a constant, which is much better than linear. Okay. Now I'm just using this to make the point that in this case, we want to talk about the average time complexity. You have to assume a model. What is the distribution of the input? And different distribution would give you different average time, which is naturally so, right? If the distribution said that those that make the algorithm run slower happen more often, then sadly your algorithm would run slower, okay? But if the distribution is that a good case happen most of the time, then algorithm would run faster, okay? All right, so I will stop here today, and the next time we'll continue with this discussion. Okay, again, starting from next week, we're going to talk about designing algorithm for real problems. Okay. All right, that's all for today. Again, feel free to ask me if you have questions. Send me email, go to them. Okay, let me just